All right. So what we have, what the project is that we need to classify audios, right? And what you guys did in your assignment was feature engineering. You extracted some features from audio data sets. You figured out which audio features can be used to classify that data. And now we are going to see how to create a very simple traditional model that will help us classify those audios. Okay, so what we are going to use today are traditional machine learning algorithms. There are two kinds of algorithms. The first one are traditional, and the second one are your neural networks. Okay, our project will basically be based on the neural network part, but I need to show you guys how traditional ones work, because traditional ones are the ones that require feature engineering. Okay, see, the second point here is that they require feature engineering. The features you extracted from your audio files, they are put in these machine learning algorithms, and then these models classify them based on those particular features. This is different from your neural networks, because in neural networks you can just add the raw data to it. Okay, you do not need to extract any feature, you can just give it the data and it will classify it. Okay, that is a very very good part of neural network. So if you try to find on Google or on YouTube, if you try to find some models for audio classification, you'll always find deep neural networks or deep learning methods that will be used to classify them. Traditional methods are generally not used to do that, and we will see why. Okay, one more thing about them is that they have a very shallow architecture, which means when you are thinking of a neural network, it means that there are a lot of neuron-like structures there, and they are interconnected with each other. Okay, and those interconnections are very complex at times. The bigger your network is, the more complex is the interconnection, and it is not very easily understandable. But in traditional machine learning algorithms, you can understand the maths behind it. Okay, you can manually check if that is correct or not. This is this part. The fifth point is um, that if you get a certain output, you can always go back and check why are you getting that output. They are not very computationally intensive, so you can go back and check it. But neural networks are generally called black boxes. So they are you give an input, that input goes into a black box. You don't know what is happening inside that box, but somehow you are getting an output. And most of the time, if implemented correctly, that output is very, very, very accurate. Okay. Oh, and traditional ML algorithms work better on a smaller data size. You see ChatGPT. ChatGPT is also made using machine learning, but that could not have been possible with this traditional machine learning algorithms. Okay, because it has so much data inside it, it was built using neural networks. Okay, and one more thing, um, if you feed, um, if you want to add some data to your traditional ML algorithms, you are going to have to add something labeled. Okay, for example, you give some, say the 6 audios I gave you. If you want to add them into your traditional ML algorithm, you need to have a CSV file or something that tells the model that, okay, these three are the number 5, the rest of the three are the number 9. Okay, or whatever the number is or whatever it is, you need to have it labeled for traditional ML algorithms. But in neural networks, most of the time, even if these don't have a label, your neural network would still be able to identify that, okay, these are in one group, these are in another group. Okay, it can still do that. But here, a manually labeled training data is required. Now, one of the most extremely basic ML algorithm is linear regression. Okay, what linear regression does is you have your independent variables, you have one of your dependent variable that you're trying to find out, you create a plot, And then what linear regression does is it tries to find the best fit line among those points. Okay, this is the best fit line, and it is based on the distance of these points from that line. Okay, and then if you give it, for example, you give it a point here, it will go up till here, and it will predict that, okay, oh, that's funny. It will predict, okay, this is the corresponding value that you're supposed to get. Okay, that is what will happen here. Now, most of you who have done the assignment, you have seen that zero crossing rate is one very good variable that you could have used to classify the two numbers. Okay, that was a very, very good method. Now, MFCC is not very obvious. You could not have found it by the mean or by plotting a graph. That is true. But MFCC, because it has so many values in it, it has basically all the important spectral and temporal characteristics of the audio. Spectral as in frequency related, temporal as in time related. Okay, so MFCC captures all of them. So it is a very good method in order to classify data. One other important thing about MFCC is that it is very less sensitive to the changes in loudness. Okay, so if there is background noise, MFCC will not catch up on that. Okay, so that is one very good thing about MFCC. So these two are the methods that we will be using today. We will see how these two can be used to create a linear regression model, and we will see what the accuracy is that we're getting. So first of all, you import all the important libraries, there's Panda, Librosa, NumPy, and from sklearn, you import train test split. Okay, we are going to split our data into some data will be used to train the model, and then some will be used to test the model. Okay, and then there's linear regression model. It is an inbuilt function inside sklearn. You can also build it from scratch. That is not a problem if you understand the math of everything that is happening in linear regression. You can build it from scratch, but here we already have it. We are using it because for this particular project we are doing, you do not need to understand linear regression. You just need to understand the differences between these traditional methods and the one we are going to use in our project. Okay, and then there's accuracy score, because we need to find okay, how accurate is our model. We will do this for the models we build here, as well as the final model that we will build for our main project. And this classification report, this has a lot of things like F1 score, and there's a lot of things in classification report that are also used to find the accuracy. Okay, we will also learn about these evaluation metrics for our model as well, but that will happen later. Okay, so we are defining a function called extract features. Okay, and then we are giving a file here. First of all, we will, like you did in your assignment, we will first find the Y1 or SR1, these two values, and from them we will find the MFCC. We will scale it using NumPy mean, and then we will also find the zero crossing rate using the same Y1. Okay, and then we'll scale that too. First of all, here we are returning only ZCR scaled. Okay, first we will see how zero crossing rate is giving us accurate results or not. So that is our function. If whatever file we put in here, it gives us the zero crossing rate, but scale. Okay, and then there's the metadata. This is very important because since this is a traditional machine learning algorithm, we need to have this metadata that classifies the, okay, this, if the audio is named this, then it is about this number. Now here I have 500 audios, but the metadata I have is only for 100 of them. Since I had to do it manually, so I only did for 100, and I need to show. You mute yourself. हाँ कर ली ना. Okay, I'll show you what it looks like. Okay, this is what your metadata looks like. If they are labeled these numbers, then we have the number 3. And for the others, we have the number 9. So we are only doing it for 2 numbers for now. Okay. Mhm. Right. So we load that CSV file with all the content in it. We we create 2 lists, one for the features and one for the label. The features will include this ZCR scale, and the labels will include if that number is 3 or 9. Okay, that is what the labels will include. Now for index and row in this metadata, since you know that it only has 2 columns, the first one has the file name. Okay, these file names, that is what the first column has, and the second column has the label in it. Okay, so in file paths for this, we will wait, am I audible? Okay. Um, okay, so first in extract feature, we will add the file paths. Okay, whatever the names are in the column of file name in our metadata, we will put that every file name, we will keep it here in extract features, and then we will find the ZCR scale, which will be added to features. Okay, that is what is happening here. And label is equal to label. That is obvious because that is the only label we have. So we append it to our labels list. We do that. Okay, and then what is happening here is we are using the train test split. Okay, what this does is it splits your data into these 4 variables. Okay, the X values are your independent variables, the features we have. Okay, these features will be used as X train and X test. Okay, and then there's your Y train and Y test. This Y is the final output you're supposed to get. Okay, which is the label that either the number is 3 or it is 9. So that is your label. Okay. And this test size indicates that out of the 100% of your data that you have, 20% of it will be used as test data, 80% of it will be used to train the model. Okay, that is what this is about. You can change these values. It's fine. And this random state is only used so it is used to specify ki, okay, if the random state is specified as 42, the features that we get right now are the features that everyone will get. Okay, if you are sharing that. If you remove this random state, it will pick any random 20% values for the test and any random 80 for the train. But if the random state is 42, then this is always going to be what you're going to get. Okay, so it is just important when you are supposed to share that data with others. So we run this and it splits the data. If you want to see X test, you can do that as well. Wait, gaps. See, that's just your array. You can do that. You can use, you can see your train as well. Okay, these are just arrays that you have of your this ZCR scaled features. Okay, and if you see your Y train, then see, then this will have the 80% of your values for the labels. Okay, now for the model, we specify it as linear regression model. It's simple as that. And then you just do model.fit. So you fit that model into X train and Y train. Okay, X train are the features, Y train are the labels for those features. Okay, for the training ones. So we fit that model into this. Now what this will do is it will create this line, and then every feature we add here, it will give us one value here. Okay. Now we do model.predict. So we are predicting this for X test. Okay, the 20% of the data we have, we are going to predict the values for this. Now you should see. Okay. Okay, so it's only predicting 9 for everything. So clearly this is not a very good model for this. Okay, now leave this part for now. Now, if you calculate the accuracy for it, oh, what is happening? Oh, wait. So I predict. Okay, so if you calculate the accuracy, you see that it is 40% accurate, which is not a very good accuracy. And if you want the classification report, you can do that as well. See, it will give you the precision, recall, F1 score, and support. We will learn what these are later when we are supposed to um, find the accuracy of our own model that we built. Then we'll learn what these are. Okay, so for now, it has very low accuracy. It is not a good model. So we try to do something else. This support vector machine, SVM, is another classification method. What this does, it does not create a perfect fitting line. What it does is that, for example, these are the features that are there for the number 3. Okay. And these are the features for number 9. So what it will do is it will create a plane, okay, a plane or a hyperplane, and it will separate them, both of them. So the features that lie on this side of the plane, they will be classified as for the number 3, and here they will be classified as the number 9. Okay. Oh, and one more thing we needed to see here was, what if we use the MFCC? If we use the MFCC in order to classify this using the same linear regression model only, then what is the accuracy we are going to get? Okay, now see, this part was for these values, because when you're using MFCC, this, okay, since, for example, if most of your points are here for 3, some of them are here for 9, and it fits a line. So what it will do is, if you give it a point here, it will maybe say that it is 3.5. The value is 3.5. If you give it a number here, maybe it will say the value is 6.5. Okay, and so on. It won't give you accurately 3 or 9 as a result. So one way to keep it between like 3 and 9 is that you can maybe select a number, and you can say that, okay, if the value is, say, greater than 4, okay, then you can say that the value is 9. And if the value is less than 4 or equal to 4, then say that it is 3. Okay, that is what you're doing here. And if you do that, see, you get different values. Okay. And then when you measure the accuracy, it says that it is 100% accurate, which is not going to be the case always, but here somehow we have achieved that. But this is the problem, because we had to do this manually. If you keep it as, say, 3, okay, if you do 3, then you have 65% accuracy. Okay, you can just play around with it. Now the problem is, you won't always have only this much of data. You won't always know which number should you use in order to like differentiate between them. So that is a problem. Okay, like I said, traditional machine learning methods work better when you have smaller data. All right. Okay, so we try another algorithm, which is called support vector machine. One more thing, MFCC gave us way better results than zero crossing rate did. Okay. Now again, it has support vector classification as one of its function. sklearn has it. So we are going to just import it. So we don't have to write everything from scratch. We don't have to do the math. This is the same extract features that we used earlier. And we are using ZCR scaled first. Again, the same thing. We are going to extract those features and add them to two separate lists, features and labels. Again, we split the data. This time we have the test size as 0.25. The random state is still the same. You can write any number here. It's not necessarily 42. Okay, so this is what we have. Now we have to specify the kernel, and don't mind that value for now. This is what we have to specify for SVC, and then we fit the model. Okay, that is done. And now we predict. We predict here, and then we find the accuracy. Okay. Okay, so it is 44% accurate, which is again a very bad accuracy. Now, okay, now for one audio which was not there in the training or testing data, we try a new audio and we extract its features, and then we add those features in your prediction model. Okay, so we predict that, and then we print our prediction. Okay, if this is starting with 3, so the answer should technically be 3. But it is predicting 9 for it because it has only an accuracy of 44%. So it is a very bad model again. And now we try the same thing with MFCC scaled. We run all the cells again the same way. We create a model and then we predict. Okay, now the accuracy is 1, which means 100%. Now see, the accuracy was also 1 here as well when we had this as greater than 4. But the problem is that it won't always give you accurate results. Now, if you do predict it for this value, see, it's giving the correct result. But I won't try all of these values, but if you try enough values, you will see that it does not always give you the right results. Okay, at some point or the other, it is going to give you incorrect results. Since this data we have is for 500 numbers, but we only trained it on 80 of them. Okay, because 20 were used for this thing. See, it should have predicted 9 here. If it was actually 100% accurate, it would have predicted 9, but that is the problem. Okay, so what we will need to do here is that we will need to have either a very large metadata, so we can find ki, okay, we have say 15,000 values for 15,000 different audios for 3 and 9, and then we can classify them. And again, one another problem is that we only had 2 of these numbers here. Okay, now in general, we might have say 1 through 100 numbers we needed to classify. Okay, that won't be both of these won't be a very good model unless you have a lot of data and a lot of time to train your model. That is going to create a problem, and still you won't always get very nice results. It all depends on how you implement it. Yes, that is one very good point, Ashutosh. See, what overfitting is okay. For example, if say your data was not distributed like this, okay, if your data was distributed like this curve, okay, just look here, like if it is like this curve, okay, the bottom side of this curve is these blue dots for 3 say, and the upper ones are red dots for 9. So sometimes what the models do is they create this boundary they create it like this. Okay, they create this boundary, so anything that comes beyond that boundary is 9 and this side is 3. But there are many times that maybe like for the curve that is coming like this here, maybe you have a blue dot here, okay, but it is beyond that boundary, so it will classify it as 9, and that is called overfitting because it is so, like, it is fitting the model so accurately that any small deviation will give you incorrect results. Okay, any small variation and your model will stop working. It will give you inaccurate results and it won't work then. So that is also a problem that we get when we are using these traditional models. That is also something we need to see when you're using this. Okay, so this here is done. Now what I am going to do is I am going to give you the resources that tell you how neural networks work, what exactly they are, and how we are going to use them in order to classify our audios. Okay, it the theory might be a little overbearing for you, but try to understand it in simple terms. And if you don't understand any part of it, ask me and I'll help you out. Um, okay, but from this point onwards, it is extremely important for you guys to focus on the theory, to understand how neural networks actually work. Because if you don't understand how they work, you won't be able to understand when we build the model, what is happening, and then you will feel lost, and then you'll want extra time. Okay, and I won't be able to give it to you then. The third, since our third week is starting, third week of the project, we are going to build a small neural network model to classify audios. That is the next assignment that I will give you maybe next week, Saturday, Sunday, sometime. So you still have plenty of time. So until then, all you need to do is focus on the theory, understand how these things work, and then I'll show you a simple model, how it is built, like I showed you these two models. I'll explain you each and every line of them, and then you'll build the same model with some tweaks or some new things that you might learn along the way. And the measure for the evaluation will be based on the accuracy of your model. Okay, so it has to be a very good model. I don't expect it to have, say, 95% accuracy, but it should definitely be above 60. Okay, because for now, that mini model, I won't give you a very large data set. So it should absolutely have 80% above accuracy, but I'll keep the threshold till 60. Okay, since it's many of you are building it for the first time, so I'll keep it till 60. And if you don't have any questions, you guys can leave. I have taken your attendance. And just remember that if you guys can cope up with the resources and project, please do that before the end of December. I cannot extend the timing for all of you guys. Yes, Samartha, absolutely. I will do that by tonight. I'm just waiting. So the people who have not yet submitted the second assignment, they do that. And then I'll share the marks of both of them. No, not yet. I will be sharing them by end of day today after I have graded the second assignment as well.